CERN was built to find the smallest particles in the universe, but for just 100 nanoseconds. It may have captured something that did not belong to our timeline. The signal did not match any known particle, could not be recreated by simulation, and appeared like two overlapping traces hidden inside the data. Before we go deeper, like and subscribe, because if this data is real, CERN may not have just detected matter, it may have touched the edge of another reality. Get ready, we begin now. There is a tunnel buried 100 meters beneath the Swiss-French border, running in a perfect circle 27 kilometers around. Inside it, protons particles so small that lining up a billion of them side by side would barely span the width of a grain of sand are accelerated to 99.9999991%, the speed of light. Not approximately, not roughly, 99.9999991%. When those protons collide, the energy released at the impact point is equivalent to 10,000 lightning bolts striking simultaneously on a spot smaller than an atom. Not a small atom. Smaller than the nucleus of an atom. For a fraction of an instant, that single microscopic point becomes hotter than 100,000 solar cores layered on top of each other, briefly recreating conditions that last existed in the universe approximately 1/1,000,000th of a second after the Big Bang itself. This is the Large Hadron Collider, the most complex scientific instrument ever constructed by human civilization. 10,000 scientists from over 100 countries contributed to its design and construction. The superconducting magnets that bend the proton beam must be cooled to -271.3 degrees Celsius, colder than the open void between galaxies, just to maintain operational function. The engineering tolerances are smaller than the width of a human hair, spread across the full 27-kilometer circumference. Atlas, one of its two primary detectors, stands as tall as a 5-story building. CMS, the other, weighs more than 30,000 tons heavier than the Eiffel Tower by a significant margin. Every component, every calibration, every adjustment, the product of decades of accumulated human precision, tested and retested, verified and re-verified. By any honest measure, the LHC is the pinnacle of what scientific civilization has so far managed to build, which makes what happened in 2015 extraordinarily difficult to set aside. That year, CERN completed a major operational upgrade, what physicists designated Run 2. The previous phase had pushed collision energies to 8 tera-electron volts. Run 2 pushed that number to 13 tera-electron volts, eventually reaching 13.6. To translate that into plain language, the machine crossed into an energy range that had never been physically achieved in any controlled experimental setting in the entire history of human science. Theoretical models had mapped this territory for decades. No instrument had ever physically touched it. The detectors Atlas and CMS were upgraded accordingly. Sensitivity was sharpened. Data pipelines were expanded and stress tested. Every system was calibrated, then recalibrated a second time. The teams had spent years preparing. They were ready for surprises, that is, after all, the entire purpose of building such a machine in the first place. What appeared in the early operational runs of 2015 was a surprise of a categorically different kind. The internal term used among detector specialists was ghost hits. In particle detector systems, a hit is a signal, a particle passing through a detector layer and leaving a measurable electronic trace. Every known particle has a distinct signature. Electrons behave one way, muons behave another. Quark jets fragment with predictable energy distributions that the software has cataloged in extraordinary detail. The entire detection apparatus functions essentially as a fingerprint database for subatomic matter, and the algorithms know every fingerprint that physics has ever confirmed. These signals matched none of them. They appeared in both the Atlas and CMS detector systems during the early runs of 2015. They lasted approximately 100 nanoseconds, 1/10 millionth of a second. And that specific duration is far more significant than it might initially appear. Electronic noise in large detector systems, the kind generated by stray electromagnetic interference, thermal fluctuations, or background radiation, typically manifests across timescales of a few nanoseconds or less. It is messy by nature, inconsistent, scattered across channels without coherent shape or repeatable structure. Random noise does not sustain a consistent duration. It does not arrive with organized internal characteristics. 100 nanoseconds, appearing with a defined and repeatable shape in the energy distribution, is not random noise. The duration alone rules that out. But it is also not a mechanical failure. Mechanical faults in detector systems, misaligned components, degraded sensor elements, cooling irregularities produce signals that are slow in onset, gradual in development, and distributed across multiple adjacent channels in traceable, correlated patterns. These ghost hits didn't behave that way either. They were sharp, localized, structured. The engineering teams ran simulations, systematic, thorough, methodical simulations modeling every known source of spurious detector response, beam-related backgrounds, cosmic ray, muon contamination, secondary particles from beam gas interactions, cavern radiation. Every candidate explanation that existing physics could offer was fed through the simulation pipeline and compared against the recorded data. None of them reproduced what the detectors had actually captured. And then there was the shape of the signal itself, which made it stranger still. The ghost hits carried a double peak structure in their energy distribution, a bimodal pattern, not a single peak, as every known particle process produces, but two overlapping peaks, suggesting not one source, but two independent sources generating the same class of event at the same moment. The standard model of particle physics, which accounts for every confirmed subatomic particle and every known fundamental force. With predictive precision extending to 12 decimal places in some measurements, has no mechanism that produces this. No process in the current theoretical framework generates a bimodal signature from a single collision event. The model simply doesn't have a category for it. Picture this. You are filming an empty room, door locked from the outside, no windows, no objects inside bare walls under steady light. The camera runs for a full hour without incident. Then, for exactly 1/10 millionth of a second, the frame captures a shadow on the far wall. Not a smear from a passing headlight outside, not a lens artifact. A shadow with defined edges, a recognizable shape, holding just long enough to be unambiguous and then gone as cleanly as it arrived. Do you mark the file "camera malfunction" and delete it permanently? Or do you sit down and ask who cast that shadow? The LHC's data systems faced a version of that exact choice. And the decision was made by the algorithm before any human scientist could formally raise the question. The trigger and data acquisition system at the LHC processes approximately 40 million proton-proton collisions every single second. 40 million. Of those, the system selects roughly 1,000 per second to actually record and store for analysis approximately 0.0025% of everything that physically occurs inside that tunnel. The remaining 39,999,000 events are discarded permanently, in real time, because no data infrastructure on the planet could hold 40 million fully resolved collision records per second. The selection is made by automated algorithms, fast, decisive, built entirely on criteria derived from standard model physics from known particles, known decay signatures, known energy patterns. If a signal does not resemble something the algorithm was trained to recognize as worth keeping, it does not survive. It is gone before any human eye could ever review it, permanently and irretrievably gone. So here is the question that never appeared in any published paper, never reached peer review, never became a formal line of investigation anywhere in the collaboration of the tens of millions of collisions erased every second. How many contained ghost hits that no physicist ever had the chance to examine? You might be thinking surely the engineers would have caught this. Surely a signal that strange would have triggered an investigation. And that instinct is reasonable. But here is what makes it uncomfortable. The same system designed to find the unknown was, by engineering necessity, built to automatically discard anything it didn't already know how to recognize. A detective agency that hired an assistant with one firm instruction report. Only the clues that look familiar. Everything unrecognized goes directly into the shredder. Efficient, certainly. But if the most important clue in the case happens to be one nobody has seen before, that assistant will destroy it without a second thought, file a clean report, and go home early. But the 100 nanosecond ghost signal was only the opening act. The truly strange anomaly was hiding deeper in the data, buried inside the 4-lepton channel. And it didn't appear just once. In particle physics, not all decay channels are created equal. Some are loud and messy, dozens of particles flying outward in every direction, overlapping signals, backgrounds so thick that finding anything meaningful inside them requires years of statistical untangling. Others are clean, quiet, almost surgical in their precision. The 4-lepton channel is the cleanest of all. When certain particles decay, they occasionally produce exactly 4 leptons electrons or muons as their final measurable products. No hadronic mess, no overlapping jet contamination. Just 4 charged particles, each leaving a sharp, unambiguous track through the detector. The background processes that could mimic this signature are few and well understood. When something unusual appears in the 4-lepton mass spectrum, it stands out the way a single voice stands out in an otherwise empty concert hall. You don't need to strain to hear it. You just need to be paying attention. This is precisely the channel that Atlas and CMS used in 2012 to confirm the existence of the Higgs boson, the particle that took nearly 5 decades to find after Peter Higgs and Francois Englert first theorized its existence in 1964. July 4th, 2012, Geneva. The auditorium at CERN filled with physicists, some of whom had spent their entire careers working toward this single moment. Peter Higgs himself sat in the audience, visibly emotional. When the Atlas and CMS spokespersons presented their combined results, a sharp, unmistakable peak at 125 giga-electronvolts in the 4-lepton mass distribution. Registering at 5 sigma statistical significance, the room erupted. People wept. Decades of theoretical work, billions of dollars of engineering, and the meticulous labor of thousands of scientists had converged on one clean spike in a graph. The Nobel Prize in Physics followed in 2013, awarded jointly to Higgs and Englert. The 4-lepton channel had delivered the most celebrated discovery in modern particle physics. It had earned its reputation as the gold standard of detection. Clean, reliable, unambiguous, which is exactly why what appeared in the Run-2 dataset was so deeply unsettling. During internal analysis of the Run-2 data, the dataset collected after the 2015 upgrade to 13 tera-electronvolts, physicists examining the 4-lepton mass spectrum found something that was not supposed to be there. Not at 125 giga-electronvolts, where the Higgs sits. Somewhere else? A statistical clustering in a different region of the mass spectrum, at an energy value that corresponded to no known particle, no predicted resonance, no anticipated background process in the standard model. That alone would have been noteworthy. Unexpected bumps in mass spectra are not unheard of. The history of particle physics is littered with tantalizing statistical fluctuations that eventually dissolved with more data. But this anomaly carried an additional feature that separated it from every previous unexplained bump in the literature. The signal had a bimodal distribution, 2 peaks, not one. A double structure in the mass spectrum, as though 2 independent sources were simultaneously generating the same class of 4-lepton event at the same collision energy. The standard model contains no process capable of producing this. Not a known particle decaying through 2 separate pathways simultaneously. Not a background contamination, those had been modeled and subtracted. Not a detector artifact, the signal appeared independently in both ATLAS and CMS. 2 entirely separate instruments built by different teams using different technologies, positioned at different points around the 27-kilometer ring. Both detectors saw the same double structure, at the same energy, in the same channel. Drop a stone into a still pond. 1 stone. What do you see? 1 set of concentric ripples expanding outward from a single point. That is the only physically permitted outcome. 1 source, 1 wavefront, 1 origin. The mathematics of wave propagation does not allow for 2 independent centers of disturbance from a single impact. What CERN's detectors were recording in the 4-lepton channel was the equivalent of dropping 1 stone and watching 2 completely separate sets of concentric ripples expand simultaneously from the same point of impact. 2 wave fronts, 1 stone. That doesn't just challenge what you know about wave physics, it breaks it at the foundation. In quantum mechanics, the concept of superposition describes a particle existing in multiple states simultaneously. Before measurement forces it to commit to one, an electron can spin up and spin down at the same time. A photon can travel 2 paths simultaneously. This is not a metaphor or an approximation. It is the experimentally confirmed, mathematically precise behavior of matter at the subatomic scale. But superposition is supposed to collapse instantly, completely, the moment a system large enough to constitute a measurement interacts with it. A particle detector the size of a 5-story building filled with trillions of atoms absolutely constitutes a measurement. At the tera-electronvolt energy scale, in a macroscopic detector surrounded by a dense electromagnetic environment, quantum superposition should not survive long enough to leave a measurable signature in the data. And yet the data showed what appeared to be exactly that: 2 quantum states, 2 source signatures, occupying the same event simultaneously. As if something at the collision point had briefly existed in 2 distinct configurations at once, each configuration leaving its own imprint before decoherence erased the boundary between them. 2 timelines, 2 states, 1 detector reading, recorded in the cleanest, most reliable channel in experimental particle physics. The statistical deviation reached approximately 2.8 sigma before the dataset was reclassified and the analysis pipeline was closed. For context in particle physics, 3 sigma is the threshold for calling something evidence. 5 sigma is the threshold for calling something a discovery, the standard used when ATLAS and CMS announced the Higgs boson in 2012. 2.8 sigma is not noise, it is not nothing. It is a result that, in any normal scientific workflow, triggers deeper investigation, calls for more data collection, demands independent verification from a second team. If the analysis had continued, if the run-to dataset had been extended, and the signal had held it needed only to grow from 2.8 sigma to 5 sigma to become, by the field's own standards, an official discovery, the most significant discovery in the history of physics, someone stopped counting before the finish line? In particle physics circles, there is an informal but universally understood hierarchy of language. 5 sigma means discovery. Below that is evidence. Below that is interesting hint. And below that, apparently, is instrumental artifact, the classification applied when the institutional appetite for an answer runs out before the data does. In the community that spent 48 years and billions of dollars hunting the Higgs boson through this exact channel, The idea that a 2.8 sigma bimodal anomaly in the 4-lepton spectrum is simply a detector glitch is not a scientific conclusion. It is a decision dressed up as one. The ghost hits in Part 1 could at least be partially attributed to the ambiguity of noise timescales. This was different. This was a structured statistical anomaly in the most trusted detection channel in the field, confirmed independently by 2 separate instruments, carrying a physical signature that the standard model cannot produce, and it was labeled a malfunction. But labeling something a malfunction and closing the file is not the end of the story. It is only the beginning of a different, darker one. Because that label was not a scientific judgment, it was an administrative decision. And administrative decisions, unlike physics, always leave a paper trail. Every result that comes out of CERN follows the same path, no exceptions. Raw detector data is processed and cleaned, then written up as an internal note circulated within the collaboration. If the internal note survives scrutiny, it becomes a CERN technical report, a formal document with a reference number, permanently archived and publicly accessible. From there, it moves to an R-Mark-Eve preprint, posted openly for the global physics community to read and critique before formal submission. Finally, it goes through peer review at a journal Physical Review Letters, the European Physical Journal, or similar, where independent referees examine the methodology, the statistics, and the conclusions. The entire pipeline was designed with one explicit purpose: to make sure that no single person, no single group, and no single institutional interest can quietly bury a result. Every step creates a paper trail. Every step requires more eyes. The system is, in principle, a machine for enforcing transparency. That principle and the practice that followed in the aftermath of the Run 2 anomaly are 2 entirely different things. Instrumental artifact is a legitimate term in experimental particle physics. It has a precise meaning: a detector noise spike caused by a failing electronics channel instrumental artifact, a spurious signal produced by a cosmic ray muon passing through the cavern at the wrong angle instrumental artifact, background contamination from beam gas interactions leaving tracks in the wrong region of the detector instrumental artifact. But the term has rules. To classify something as an instrumental artifact, you need to satisfy specific conditions. The signal must be reproducible through known physical mechanisms. You must be able to demonstrate, through simulation or controlled testing, exactly how the detector produced it. The artifact must have a clear origin, a specific hardware component, a documented failure mode, a background process with a known cross-section. And critically, the classification must go through the same internal review process as any other result. It must be written up, circulated, challenged, and confirmed. None of that happened with the Run 2 bimodal anomaly. No CERN technical note with a public reference number was ever filed describing the specific hardware mechanism responsible for producing a bimodal distribution in the 4-lepton mass spectrum. No simulation study demonstrating how any known detector failure mode generates a double peak structure at that energy was ever circulated through the collaboration. The classification that was applied and the phrase used in internal communications to describe the anomalous clustering was structured background of unknown origin. Read that phrase carefully. Structured background of unknown origin. That terminology does not exist in the standard lexicon of either the ATLAS or CMS collaborations. It appears in no published methodology paper, no detector performance study, no data quality framework document that either collaboration has made public. It is a category that was, in effect, invented for this occasion, broad enough to contain the anomaly, vague enough to require no further explanation, and positioned just outside the pipeline that would have forced a formal investigation. Before any result from ATLAS or CMS reaches publication, it passes through approximately 500 internal reviewers. 500. The collaboration review process involves working groups, editorial boards, statistics committees, and final sign-off from the collaboration spokesperson. A single analysis can take 2 to 5 years from initial observation to published paper precisely because that many people are examining it from that many angles. The anomaly never entered that pipeline. It was handled at the data quality assessment stage before the analysis was formally opened, before a working group was assigned, before the 500 reviewers ever had a chance to see it. The classification was made upstream of the entire review process, which meant the review process never activated. Technically, no rule was broken. The system functioned exactly as designed. And that is precisely the problem, because the system, as designed, contains a gap wide enough to swallow an anomaly of any size, provided the classification happens at the right stage. When a result has no physical mechanism to explain it, calling it a lapse in instrument behavior is not a conclusion. It is an assumption wearing the costume of a conclusion. And in science, assumptions that bypass the verification process are not findings. They are decisions. Imagine a radiologist reviewing a chest X-ray. In the lower left lobe, there is a shadow, small irregular edges, not consistent with the surrounding tissue density. The radiologist types into the patient's chart artifact from imaging equipment and closes the file. No second scan ordered, no consultation with a colleague, no check of the machine's calibration log, no follow-up appointment scheduled for the patient. Would you call that a medical judgment? Or would you call it a choice to avoid the implications of what the image might actually show? The radiologist may be right. It genuinely could be a scanner artifact, but the professional and ethical obligation in medicine is not to assume the benign explanation. It is to rule out the dangerous one first. The same standard should apply to physics. When an anomaly appears in your most trusted detection channel, confirmed by 2 independent instruments, carrying a physical signature that your theoretical framework cannot account for, the obligation is not to find the fastest path to a comfortable label. The obligation is to investigate. That investigation never happened. Over 17,500 scientists from more than 100 countries are currently working with LHC data in some capacity. 17,500. These are not passive observers. They are active researchers, most of them affiliated with universities and institutions that operate independently of CERN's administrative structure. Many of them have the technical capability to perform their own analysis of the 4-lepton mass spectrum using publicly released datasets. CERN does release processed data through its open data portal, a fact the organization frequently cites as evidence of its commitment to transparency. So why has not a single one of those 17,500 scientists published an independent analysis of the bimodal anomaly in the Run2 4-lepton channel? Think about what that silence actually requires. It requires that every physicist with access to the data and the capability to analyze it either did not notice the anomaly, decided independently that it was unworthy of investigation, or understood without anyone needing to say it directly that pursuing it was not a path that led anywhere professionally useful. 17,500 people, 0 publications, on an anomaly in the cleanest channel in the field, confirmed by 2 detectors, sitting at 2.8 sigma. In science, silence sometimes communicates more than a 40-page paper with 300 footnotes ever could. But the story of that silence does not stop in Geneva. It extends outward into the entire institutional architecture of modern physics. Running the Large Hadron Collider costs approximately $1 billion per year. That figure covers operations, maintenance, staffing, computing infrastructure, and the continuous cryogenic systems required to keep the superconducting magnets at operating temperature. The high-luminosity LHC upgrade, currently under construction with first operations targeted for 2029, carries an additional price tag of 950 million Swiss francs, roughly equivalent to $1 billion and 50 million US dollars. The entire CERN program is funded by 23 member states, each contributing according to their gross national income, with the largest shares coming from Germany, France, the United Kingdom, and Italy. $1 billion per year, 23 governments writing checks, a decade-long upgrade already in progress. That financial architecture is not incidental to the story of what happened to the anomaly data. It is central to it. When an institution receives funding from 23 governments for a specific scientific program built on a specific theoretical framework in this case, the exploration and extension of the standard model of particle physics anomaly data that calls the foundational framework itself into question does not represent a scientific problem. It represents an institutional crisis. A scientific problem has solutions, more data, better analysis, revised models. An institutional crisis has a different set of pressures entirely. Budget justifications, political commitments, the careers of thousands of people whose professional identities are built on the validity of the program they are working within. When those two things collide, genuine anomalous data and the institutional weight of a $1 billion per year program, the outcome is rarely determined by the physics. This is not a claim that CERN leadership is corrupt, or that specific individuals made deliberately dishonest choices. The mechanism is subtler and more systemic than that. It operates through incentive structures that nobody designed with malicious intent, but that produce predictable outcomes regardless. A junior researcher at Atlas or CMS needs publications to advance. Publications require collaboration approval. Collaboration approval is controlled by working group leaders and editorial boards, who operate within a culture shaped by the priorities of the collaboration leadership. No formal policy document says, "Do not investigate anomalies that challenge the standard model." Nothing is written down, but a junior physicist is not naive. They can read the temperature of a room. When leadership classifies a dataset anomaly upstream of the review pipeline, and the subject is not discussed in collaboration meetings, the message is received without anyone needing to send it. No junior researcher pushes an anomaly that leadership has effectively closed, not because they lack integrity, because pushing it would consume years of their career producing a paper that the collaboration will not approve, that journals will treat with institutional skepticism, and that will earn them a reputation as someone who pursues results that didn't check out. In academia, that reputation compounds. It affects grant applications, faculty positions, postdoctoral placements. The cost is not abstract. It is paid in professional currency that takes a decade to earn and can be depleted in a single misjudged publication. The system does not need to punish dissent. It simply needs to make dissent structurally inconvenient enough that rational actors with careers to protect choose the other path. Consider what happened with the 750 giga-electron-volt diphoton anomaly in 2015 and 2016. That anomaly, a statistically unexpected excess of events producing two high-energy photons at a combined mass of 750 giga-electron-volts, was published openly. It was discussed at conferences. It generated over 500 independent theoretical papers from physicists around the world within months of the initial release. It reached 3.9 sigma before additional data caused it to dissolve, and the field collectively concluded it had been a statistical fluctuation. That process is exactly how science is supposed to work. Observe, report, investigate, revise. The critical difference between the diphoton anomaly and the 4-lepton bimodal signal is not the statistical significance. 2.8 sigma versus 3.9 sigma is not a meaningful distinction in terms of whether something merits investigation. The difference is the nature of what each anomaly implied. The diphoton excess, if real, would have pointed to a new particle exotic, interesting, but fundamentally interpretable within the broader standard model framework. Something new living inside the existing house. The bimodal four-lepton signal implied something categorically different. It implied two simultaneous quantum states producing the same event in the same detector at the same energy. That is not a new particle inside the existing framework. That is a challenge to the framework itself, to the assumption of single-source event origins that the entire edifice of collider physics is built upon. One anomaly asked for a new room. The other asked whether the house was built on the right foundation. One was published. One was labeled a malfunction. That is not a coincidence. That is a pattern. And patterns in science are supposed to be explained, not ignored. From 2015 through 2023, CERN published more than 3,000 papers derived from Run-2 data. 3,000 papers, an extraordinary volume of scientific output, covering Higgs boson property measurements, searches for supersymmetric particles, precision tests of electroweak interactions, B physics results, and heavy ion collision studies. 3,000 papers, and not one of them contains a discussion of the bimodal anomaly in the four-lepton mass spectrum. You might call that a coincidence. You might also note that in 3,000 papers covering the same dataset, finding zero mentions of a 2.8 sigma-structured anomaly in the field's most trusted detection channel is a statistical outcome that deserves its own analysis. Transparency in science is like the terms of service agreement on your phone's apps. Everyone agrees it exists. Nobody has actually read all the way through it. And the details that matter most tend to be buried in sections nobody thinks to check. The silence may be a strategy, but the universe itself is not silent, and four completely independent theoretical frameworks are all saying the same thing in four different languages, pointing at the same place. In the history of science, the most reliable signal that something real is waiting to be discovered is not a single brilliant theory. It is convergence, multiple independent frameworks, built by different people, using different mathematics for different reasons, all arriving at the same prediction without coordinating with each other. This has happened before, and the results were decisive. In the 19th century, James Clerk Maxwell derived the speed of light from his equations of electromagnetism purely from the relationship between electric and magnetic constants. At the same time, thermodynamics was establishing fundamental limits on energy transfer through radiation. Newtonian mechanics, pushed to its boundaries, was generating paradoxes about relative motion that nobody could resolve. Three completely separate theoretical traditions, working in isolation, were all quietly pointing toward the same conclusion: the speed of light is finite, constant, and physically fundamental. Einstein did not invent that conclusion. He inherited it from the convergence and gave it a coherent home. What is happening now, with the anomaly data from the LHC and the question of what produced it, follows the same structure. Four theoretical frameworks built on entirely different foundations, using incompatible mathematical languages, developed by researchers who do not agree on each other's fundamental premises, are all predicting the same physical phenomenon, the same mechanism, the same observable signature. They call it, in various formulations, branch echoes. The first framework is the many worlds interpretation of quantum mechanics, proposed by Hugh Everett III in 1957 as his doctoral dissertation at Princeton. Everett's central argument was straightforward and radical. In equal measure, the wave function never collapses. Every quantum measurement, every interaction between a quantum system and its environment does not produce a single outcome. It produces all outcomes, each one realized in a separate branch of a continuously splitting universal wave function. In Everett's picture, every quantum event that has ever occurred has generated a branching point. The universe is not one history. It is an uncountably vast tree of histories. all equally real, all causally isolated from each other by a phenomenon called decoherence. The boundary between branches is maintained by the fact that quantum coherence between them degrades to immeasurably small levels almost instantaneously under normal conditions. Almost instantaneously under normal conditions. At collision energies of 13 tera-electron-volts conditions that have never existed in a controlled laboratory in the history of Earth. The decoherence boundary between adjacent branches is, according to extensions of Everett's framework developed by later theorists, under a form of stress it was never designed to withstand. The boundary does not break, but it thins. And when it thins sufficiently, information from the adjacent branch leaks through. A signal, an echo, a ghost in the detector that does not belong to this branch of history. The second framework arrives from an entirely different direction. In 2003, philosopher Nick Bostrom published his simulation argument in the journal Philosophical Quarterly, and physicist Max Tegmark has since developed parallel mathematical versions of the same core idea if sufficiently advanced civilizations run detailed simulations of physical reality. And if we have no way to determine whether we are in a base reality or a simulation, then statistically, we are almost certainly simulated. The physics implication, taken seriously by researchers including Tegmark at MIT, is that physical reality has a computational substrate, some underlying processing architecture that implements the laws of physics as we observe them. Under normal conditions, that substrate is invisible. Its resolution is fine enough that no experiment we can perform reveals its granularity. But a particle collider running at 13 tera-electron volts is not normal conditions. It is the most extreme stress test of physical reality that human engineering has ever constructed. If the computational substrate has limits, and any substrate must then proton-proton collisions at those energies are probing those limits directly. The anomalous bimodal signal in this framework is a rendering artifact, a moment when two computational threads handling adjacent regions of the simulation briefly interfered with each other, producing a signature that belongs to neither thread independently, but to the boundary between them. The third framework is loop quantum gravity, developed independently through the 1980s and 90s by Carlo Rovelli at Aix-Marseille University and Lee Smolin at the Perimeter Institute for Theoretical Physics. Loop quantum gravity proposes that space-time itself is not a smooth, continuous fabric. It has a discrete quantum structure at the Planck scale, approximately 1.6 times 10 to the power of -35 meters, a scale so small that no instrument has ever directly probed it. In loop quantum gravity, the geometry of space is described by a mathematical structure called a spin foam, a network of discrete quantum elements that together give rise to the continuous space-time we experience at large scales, at the energy densities produced in LHC collisions. The spin foam structure is, according to some extensions of the theory, briefly exposed, the smooth approximation breaks down, and the underlying discrete geometry becomes relevant. What that means for the anomaly is this: at sufficient energy density, the spin foam can expose what Smolin and others have called adjacent topology regions, where the quantum geometry of our spacetime is in contact with the quantum geometry of a neighboring structure in the multiverse. Not a parallel universe in the science fiction sense, a neighboring topological domain in the full quantum geometric landscape. The bimodal signal, in this reading, is the fingerprint of that contact, two geometric structures briefly overlapping in the detector's measurement space. The fourth framework is the most recently formulated, and in some ways, the most startling. In 2018, Neil Turok and Latham Boyle at the Perimeter Institute published a paper in Physical Review Letters proposing what they called a CPT symmetric universe. Their argument: the universe did not begin with a single Big Bang producing one cosmos. The Big Bang produced two, our universe, and a mirror universe running backwards in time, with matter and antimatter reversed, satisfying a perfect CPT symmetry across the pair. In Turok and Boyle's model, the two universes share a quantum boundary at the moment of the Big Bang itself. Under normal cosmological conditions, this boundary is inaccessible. It exists at energies associated with the very first instance of cosmic history, far beyond anything reachable by human technology. But the LHC at 13 tera electron volts is probing energy scales that correspond to conditions approximately 1/trillionth of a second after the Big Bang. It is not reaching the boundary, but it may be close enough that quantum information from the mirror universe bleeds through an echo from the other side of the CPT mirror, arriving in the 4-lepton channel because that channel's clean. Low background environment is the only place sensitive enough to detect it. 4 frameworks: interpretational, computational, geometric, cosmological, built on different axioms, using different mathematics, developed by researchers who disagree with each other on fundamental questions about the nature of reality. And yet, all 4 of them predict the same physical mechanism at extreme energy densities. The boundary between adjacent reality structures becomes permeable. Information leaks through. The leakage produces a signal. The signal has a specific character brief, structured, appearing in clean low background channels, carrying a bimodal energy distribution consistent with 2 overlapping sources. 4 explorers, 4 continents, 4 completely different routes through completely different terrain, and they all arrive at the same mountain. The probability of 4 independent theoretical frameworks converging by chance on the same specific observable prediction is statistically indistinguishable from 0. So the question worth sitting with is not whether the theories are right. The question is, what is it that they are all detecting? Are the theories converging, or is the evidence? Theoretical physics is, admittedly, the only field where 4 people can reach full agreement on a conclusion while remaining in complete disagreement about how any of the others got there. But when the conclusion is this consistent, across frameworks, this different, the usual rules about theoretical speculation start to feel insufficient. But branch echoes are not just a theoretical concept. There is a specific physical mechanism that explains how they occur, and it involves something you are standing on right now. You already know intuitively why the chair you are sitting in does not tunnel through the floor, why the coffee cup on your desk does not spontaneously exist in 2 places simultaneously, why the macroscopic world around you behaves in the predictable, classical way that Newton described solid, local, singular. The reason is decoherence. Quantum mechanics applies to everything electrons, atoms, molecules, and in principle to objects of any size. The equations make no distinction between a subatomic particle and a coffee cup. Both are described by wave functions. Both can, in principle, exist in superposition. The reason your coffee cup does not visibly demonstrate quantum behavior is not that it is too large for quantum mechanics to apply. It is that the environment around it, the air molecules bouncing off it, the photons from the room light scattering off its surface, the thermal vibrations in its ceramic structure is continuously measuring it, billions of times per second, in ways that instantaneously resolve any quantum superposition into a definite classical state. Decoherence is the process by which quantum possibility collapses into classical fact, and the speed at which it happens scales with the complexity of the object's environment. For a large object surrounded by a rich environment, decoherence is essentially instantaneous. This is why Schrödinger's cat is not actually both alive and dead. The cat's interaction with the air in the box, with the radiation from the detector, with every molecule in its immediate environment, decoheres its quantum state millions of times before any meaningful superposition could develop. Now, what happens when you remove the environment almost entirely? Empty space is not empty. This is one of the most experimentally confirmed and conceptually disorienting facts in modern physics. The quantum vacuum, what physicists call the zero-point field, is a seething, roiling sea of virtual particles constantly popping in and out of existence, borrowing energy from uncertainty itself for spans of time too brief to directly observe. The Casimir effect, measured in laboratories with extraordinary precision, demonstrates this directly. Place two uncharged metal plates close enough together in a vacuum, and they are pushed toward each other by the pressure of virtual particles that exist between them. The force is real, measurable, and has no explanation other than the physical reality of the quantum vacuum. The vacuum is not nothing. It is the substrate of everything. It is the medium through which all fields propagate, the ground state from which all particles emerge and into which they return. It is also, if the theoretical frameworks from Part 5 are correct, the membrane that separates adjacent branches of reality from each other. Under normal conditions, that membrane is effectively infinitely thick. The energy required to stress it enough to allow any information transfer between branches is astronomical, far beyond anything that occurs in ordinary matter, ordinary chemistry, ordinary astrophysics. But at 13 tera-electronvolts, in a space smaller than a proton, the local energy density of an LHC collision briefly exceeds anything that has existed in the observable universe since approximately 1/1,000,000th of a second after the Big Bang. That is enough to stretch the membrane. Picture yourself driving on an interstate late at night, radio on, locked onto a clear FM station out of the nearest city. The signal is clean, one station, one set of music, no interference. But as you drive further from the transmitter and closer to the edge of another station's broadcast range, a station on a frequency just slightly different from yours, something changes. For a few seconds, while you pass through the overlap zone, you hear both stations simultaneously. Two songs layered on top of each other, neither fully dominant, the audio equivalent of two realities briefly occupying the same channel. Then you drive through, and your original station returns, clean and singular. Branch echoes work on the same principle. The quantum vacuum, under the stress of a 13 tera-electronvolt collision, briefly enters an overlap zone between adjacent branches of reality. For approximately 100 nanoseconds, the duration measured in the ATLAS and CMS GHOST, hit data information from the neighboring branch leaks through the thinned membrane. Two quantum states occupy the same detector space simultaneously. Then, decoherence reasserts itself. The membrane snaps back to its normal thickness, and the signal vanishes as cleanly as it arrived. 100 nanoseconds is not arbitrary. It is precisely how long quantum coherence can survive in the extraordinarily noisy environment of a particle detector surrounded by trillions of atoms, electromagnetic fields, secondary particles, and the continuous measurement pressure of the detector material itself before the environment decoheres the echo back into a single classical state. Any longer, and the detector's own environment would have collapsed it sooner. Any shorter, and it would be indistinguishable from standard electronic noise. The duration is a fingerprint, and it matches. The theoretical predictions are more specific still. All four frameworks from Part 5 converge not just on the existence of branch echoes, but on their detailed observable properties. The echo must carry CPT symmetry. It must mirror the quantum numbers of the original event in a way consistent with the symmetry of the boundary it crossed. It must appear preferentially in low background detection channels, because high background environments decohere it before it can register, and the 4-lepton channel is the lowest background channel in the entire LHC detection suite. And it must produce a bimodal energy distribution, because the signal contains contributions from both sides of the boundary simultaneously. CPT symmetry, clean low background channel, bimodal energy distribution. Those are three independent, specific, falsifiable predictions, and the anomaly reported internally at CERN during Run 2 satisfies all three. The Standard Model currently describes 17 fundamental particles, 6 quarks, 6 leptons, 4 force-carrying gauge bosons, and the Higgs governed by 4 fundamental forces. It is the most precisely tested theory in the history of science, and it accounts for approximately 5% of the total energy content of the observable universe. 5%. The remaining 95% dark matter, dark energy, the unexplained asymmetry between matter and antimatter, the hierarchy problem, the cosmological constant, all of it sits outside the Standard Model's reach. Physicists have spent decades searching for the missing 95% by looking outward, building larger colliders, pointing more powerful telescopes at deeper regions of space, designing more sensitive underground detectors for dark matter particles. What if the missing 95% is not out there in some undiscovered corner of this universe? What if it is next door on the other side of a quantum membrane that the LHC briefly punctured in 2015, producing a signal that lasted 100 nanoseconds and was filed under structured background of unknown origin? Admittedly, that sounds like the plot of a Marvel film, but it is worth noting that Marvel hired physicists to make their multiverse storylines plausible. The physicists were not hired to write Marvel scripts. If branch echoes are genuinely occurring inside the accelerator, the next question is whether we would find supporting evidence somewhere outside the laboratory. And the answer, it turns out, is hiding in a phenomenon that millions of Americans have personally experienced and have never been able to fully explain. In 2009, a paranormal researcher named Fiona Broom attended a convention and discovered something that unsettled her in a way she could not easily dismiss. Talking with other attendees, she found that multiple people independently, without prompting, shared a clear and confident memory of Nelson Mandela dying in prison sometime during the 1980s. They remembered news coverage. Some remembered memorial tributes. A few recalled where they were when they heard the news. Nelson Mandela did not die in prison. He was released in 1990, served as president of South Africa from 1994 to 1999, and passed away on December 5, 2013, at the age of 95. Broom named the phenomenon the Mandela effect, the experience of a large group of people sharing the same specific false memory with a clarity and confidence that feels indistinguishable from genuine recollection. The name stuck, and once it had a name, examples began surfacing everywhere. The Berenstain Bears children's book series, written by Stan and Jan Berenstain, spelled Brenstein, since the first book published in 1962, is remembered by an enormous number of Americans as Berenstein, spelled with an E at the end. Not a vague impression, a firm, specific memory of the E. The Monopoly board game mascot, the monocled gentleman known as Rich Uncle Pennybags, is frequently remembered as holding a monocle to his eye. He never did. The monocle appears nowhere in any official Monopoly artwork across the game's entire history. And then there is Darth Vader's line from The Empire Strikes Back. Most people remember it as, "Luke, I am your father." The actual line, delivered by James Earl Jones in 1980, is, "No, I am your father." The word Luke is not in the scene. Cognitive psychology has well-developed explanations for all of this. False memory. The construction of confident recollections for events that did not occur is one of the most thoroughly documented phenomena in the field. Elizabeth Loftus at the University of California. Irvine spent decades demonstrating that human memory is not a recording device. It is a reconstruction. Every time you recall a memory, you are not retrieving a stored file, you are rebuilding it from fragments. And the rebuilding process is vulnerable to suggestion or inference, social influence, and the filling of gaps with plausible substitutes. Confabulation. The unconscious generation of false memories without any intent to deceive is clinically documented and neurologically understood. Social contagion of memory, in which false recollections spread through communities because people trust each other's confident accounts, is a real and measurable effect, studied extensively in both laboratory settings and real-world contexts. These are not fringe ideas. They are mainstream cognitive science, supported by decades of peer-reviewed research. The orthodox explanation for the Mandela effect is, in all likelihood, the correct one for the vast majority of cases. But then came the correlation data, and correlation, even imperfect correlation, demands an explanation, an informal but methodologically structured analysis conducted by independent researchers within online communities dedicated to anomalous phenomena. Compared the timestamps of the largest Mandela effect discussion threads across Reddit, 4chan, and several specialized forums against the published operational schedule of the LHC from 2015 through 2018. The researchers were looking for a specific pattern, whether spikes in reported Mandela effect experiences clustered in time around high luminosity LHC runs the operational periods when the machine was running at or near peak collision energy. They found a correlation of between 12 and 18% increase in reporting volume within 72 hours following high luminosity runs. Before going any further, the limitations of this finding need to be stated plainly. This is a correlation. It is not peer-reviewed. It has not been published in any academic journal. The methodology, while structured, has not been independently audited. Confounding variables, seasonal internet traffic patterns, news cycles, social media algorithm effects on content visibility were not fully controlled for. This data should not be cited as evidence of a causal relationship. It is, at best, a pattern that raises a question. The question it raises, however, is not easily dismissed by pointing at its methodological limitations, because if even a fraction of that correlation is real and not entirely explained by confounding factors, the mechanism required to produce it would be extraordinary. Memory, as neuroscience understands it, is not stored the way a photograph is stored on a hard drive. A photograph is a fixed arrangement of pixels that retrieves identically every time you access it. Memory is a network, a pattern of synaptic connections distributed across multiple brain regions. Primarily, the hippocampus for initial encoding and the cortex for long-term storage. Every time you recall a memory, the brain does not retrieve a stored copy. It reconstructs the experience by reactivating that network. And the reconstruction is influenced by your current emotional state, your recent experiences, and the context in which you are remembering. This is why eyewitness testimony is notoriously unreliable. This is why your memory of a childhood birthday changes subtly each time you revisit it. The network is live. It updates. Now consider this if the quantum probability landscape of the vacuum, the underlying field that governs the statistical behavior of quantum events, were shifted even slightly by the perturbation produced by a 13 tera-electronvolt collision environment. What would happen to memory consolidation? Memory consolidation occurs primarily during sleep. The hippocampus replays the day's experiences and transfers them to cortical long-term storage through a process called hippocampal cortical transfer. The synaptic strengthening that makes memories durable. Long-term potentiation involves ion channel behavior, neurotransmitter release, and protein synthesis at the molecular level. These are processes that, at their most fundamental description, are governed by quantum mechanical probability distributions. If those distributions were nudged, not dramatically, not enough to alter behavior or produce hallucinations, just enough to bias the collapse of quantum states during memory consolidation, By a fraction of a percent, the reconstruction of uncertain memories could drift, not toward random errors, toward consistent errors, biased in the direction of the shifted probability landscape. Think of it this way. A memory is like a painting that gets repainted every time you look at it, not a photograph you retrieve. If the quantum colors available to the painter shift by 0.001%, the repainting is slightly different from the original, and you would never know, because the only version you have access to is the repainted one. If that correlation of 12 to 18% represents a real causal relationship, and to be clear, that is a very large conditional, then every time CERN runs at full power, the memories of millions of people across this planet are being quietly edited without their knowledge, without their consent, and without any institution having asked whether that is acceptable. Think about that for a moment, not as a physics abstraction, as something personal. Your memory of where you were on a specific day, your memory of a conversation with someone you loved, your memory of a detail that matters to you, potentially drifting, invisibly, while a machine in Switzerland runs its scheduled high-luminosity fill. At least when Mark Zuckerberg edits your newsfeed, he is legally required to post a privacy policy update 47 pages long, in a font size that requires reading glasses, with the relevant clause buried on page 31. Nobody at CERN is filing that paperwork. But suppose you reject the Mandela effect entirely. That's completely fine, because the signs of a thinning reality membrane are showing up in the most serious laboratories in the world, with data that is not so easily dismissed. Long-term potentiation. Most people outside neuroscience have never heard the term, but it is the molecular foundation of every memory you have ever formed. When neurons fire together repeatedly, the synaptic connections between them strengthen. The receiving neuron becomes more sensitive to signals from the sending neuron, lowering the threshold for future activation. This is LTP, first described by Terje Lomo in 1973, and it is the cellular mechanism by which experience becomes memory. The process is not instantaneous. Fresh memories are fragile, held initially in the hippocampus in a labile, easily disrupted state during sleep, particularly during slow-wave sleep and REM cycles. The hippocampus replays the day's experiences and transfers them to distributed cortical networks for long-term storage. This hippocampal cortical transfer is the consolidation process. It is also, critically, a window of vulnerability, a period during which the memory is actively being reconstructed and is susceptible to modification. This is established, confirmed, textbook neuroscience. None of it is controversial. The reason it matters here is that consolidation is not just a biological process. At its deepest level, it is a physical process, and physics, at the molecular scale, is quantum mechanics. Quantum biology is one of the fastest growing intersections in all of science, and it has been producing results that would have seemed frankly implausible 2 decades ago. In 2007, Graham Fleming and his team at the University of California, Berkeley, published a landmark paper in Nature, demonstrating that photosynthesis in green sulfur bacteria uses quantum coherence to transfer energy from light-harvesting antenna complexes to reaction centers with an efficiency approaching 95%. Classical physics predicts that random thermal diffusion would achieve efficiencies far below that. The plants are using quantum superposition energy existing in multiple pathways simultaneously to find the most efficient route. It is not a metaphor. It is a measured physical effect, confirmed by multiple subsequent studies. Bird navigation offers an equally striking example. The European robin and several other migratory species navigate using the Earth's magnetic field with a precision that classical chemistry cannot explain. Research at the University of Queensland and other institutions has established that the mechanism involves quantum entanglement within cryptochrome proteins in the bird's retina radical pairs, whose quantum spin states are sensitive to magnetic field orientation at levels far below what any classical chemical reaction could detect. The bird is, in a very real sense, using entangled quantum states to read a compass. Enzymes accelerate chemical reactions by factors of up to 1 quadrillion compared to uncatalyzed rates. A significant portion of that acceleration, research has shown, is achieved through quantum tunneling particles passing through energy barriers that classical mechanics says they cannot cross. The enzyme is not just a chemical scaffold, it is a quantum mechanical device. Life, it turns out, has been doing quantum computing for billions of years. The brain, which is the most metabolically active and electrochemically complex organ in the known universe, is not exempt from this. In 1994, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed what they called orchestrated objective reduction, or ORCH-OR, a theory that quantum computations occurring in microtubules within neurons contribute to conscious experience and cognitive processing. The theory has been controversial since its inception. Many neuroscientists have challenged it, and the debate remains genuinely unresolved. What has not happened is a definitive refutation. In 2022, a research group led by Travis Craddock, building on earlier work, published findings demonstrating measurable quantum coherence in tubulin proteins, the building blocks of microtubules at physiological temperatures, body temperature, 37 degrees Celsius. The long-standing objection to ORCH-OR had always been that the brain is too warm and too wet for quantum coherence to survive long enough to matter. That objection is now significantly weakened by experimental data. Quantum effects in the brain are not confirmed, but they are no longer dismissible. Now construct the chain. The LHC perturbs the quantum vacuum at 13 tera electron volts. The quantum vacuum is the universal field that underlies all quantum probability distributions everywhere on Earth. Simultaneously, it is not a local phenomenon. If that perturbation propagates through the vacuum field, even at an extremely attenuated level, it shifts the probability landscape governing quantum events globally. Memory consolidation during sleep involves molecular processes, ion channel gating, neurotransmitter vesicle fusion, protein folding during synaptic remodeling that are subject to quantum mechanical probability distributions. If those distributions are shifted by a perturbation in the vacuum field, the collapse of quantum states during consolidation is biased, not dramatically, not enough to produce new memories from nothing, or to erase existing ones, but enough to introduce a consistent drift in the reconstruction of memories that are already uncertain details that the brain was going to fill in probabilistically anyway, now filled in slightly differently because the underlying quantum probabilities have shifted. The drift would not be random. It would be directional biased by the specific character of the vacuum perturbation. And because every human brain on the planet shares the same quantum vacuum field, the drift would be collective. The same details would shift in the same direction for millions of people simultaneously. Not because those people communicated with each other, because they are all running on the same underlying quantum substrate, and that substrate just got nudged. That is why the Mandela effect, if it has a physical component at all, would be collective rather than individual. Random false memories from individual cognitive errors scatter in every direction. Collective false memories sharing consistent specific details, the same spelling, the same misremembered line, the same misplaced logo point toward a systematic bias in the reconstruction process. Every link in that chain has independent scientific support. Quantum vacuum perturbation at LHC energies, supported by the theoretical frameworks of Part 5. Quantum effects in biological systems demonstrated in photosynthesis, bird navigation, and enzyme catalysis. Quantum coherence in neural proteins at body temperature measured at Sapienza University in 2022. memory consolidation as a reconstructive process vulnerable to quantum-level influences consistent with everything neuroscience knows about LTP and hippocampal cortical transfer. The chain is long. Each link is a conditional. It may be entirely wrong. But there are over 8,000 peer-reviewed academic papers studying false memory from the perspective of cognitive psychology, examining social contagion, suggestion effects, encoding failures, and retrieval distortions. The number of peer-reviewed papers investigating a potential relationship between quantum vacuum perturbation and collective memory drift is, for all practical purposes, 0. We are not failing to find the answer. We are declining to ask the question. The only known instance in history where the explanation for "why did I remember that wrong" might conceivably be because a 27-kilometer machine in Switzerland was firing protons into each other at 3 in the morning, and the scientific community has collectively decided that this particular line of inquiry is not worth a single formal investigation. The clues about a thinning reality membrane are not coming only from CERN or from human memory. They are emerging from entirely different experiments in places nobody would have thought to look. A muon is, in most respects, an unremarkable particle. Think of it as an electron's heavier, shorter-lived cousin, identical in charge, identical in spin, identical in how it interacts with electromagnetic and weak forces, but 207 times more massive. It lives for approximately 2.2 microseconds before decaying into an electron and 2 neutrinos. And then it is gone. In the grand catalog of fundamental particles, the muon occupies a modest position. Nothing about it suggests it should be the instrument that cracks open one of the deepest problems in modern physics. And yet, every charged particle with a quantum spin possesses what physicists call a magnetic moment, an intrinsic magnetism generated by the particle's fundamental nature, not by any external current or motion. For the muon, this magnetic moment is quantified by a dimensionless number called E. The value of G for a perfectly simple non-interacting particle would be exactly 2. But particles do not exist in isolation. They interact continuously with the quantum vacuum, the churning sea of virtual particles described in Part 6, and those interactions nudge the value of G away from 2 by a tiny but precisely calculable amount. The Standard Model calculates this nudge, called the anomalous magnetic moment, with a precision that extends to 12 significant decimal places. It is the most accurate theoretical prediction in the history of science. Not approximately accurate, not accurate within reasonable margins, accurate to 12 decimal places, a level of precision that makes the engineering tolerances of the LHC look rough by comparison. The predicted value 0.00116591810. The muon G2 experiment at Fermi National Accelerator Laboratory outside Chicago began its first data collection run in 2019, with initial results announced in April 2021 and a major updated analysis released in August 2023. The experimental apparatus is a storage ring, 14 meters in diameter, a precisely engineered circle of superconducting magnets that holds muons in a circular orbit while measuring, with extraordinary care, how their magnetic orientation precesses as they travel. The measurement precision achieved was plus or minus 0.20 parts per million. The measured value 0.00116592061. Write those two numbers side by side, and the difference looks trivial, a deviation appearing in the 10th decimal place. In absolute terms, it is a number smaller than anything with obvious physical meaning in daily life. But in the language of particle physics, where every decimal place has been earned through decades of theoretical calculation and experimental refinement, that deviation is not trivial. It is catastrophic for the model that predicted it. The combined statistical significance of the Fermilab result with the earlier measurement from Brookhaven National Laboratory, a separate experiment completed in 2006, reaches 5.1 sigma. 5.1? That is the discovery threshold. By the field's own standards, this is not a hint, not evidence, not an interesting anomaly awaiting confirmation. It is a confirmed discrepancy. The standard model's prediction is wrong. Something is pulling the muon's magnetic moment away from where all known physics says it should be. The question is what? And that question has no answer within the current framework. The muon's anomalous magnetic moment reflects the totality of its interactions with the quantum vacuum. Every particle that exists, every field that operates in the fabric of space, leaves a fingerprint on that value through virtual interactions. The standard model's prediction accounts for every known particle and every known field. If the measured value disagrees with that prediction at 5.1 sigma, the most straightforward interpretation is that the muon is interacting with something the standard model does not contain. A particle not yet discovered, a field not yet theorized. And this is where the story reconnects with everything that came before a contribution from a quantum vacuum that is not quite as empty or as singular as the standard model assumes. If the vacuum contains echoes from an adjacent branch of reality, as the four theoretical frameworks of Part 5 predict, those echoes would carry energy and momentum. They would interact with particles traversing the vacuum. And the muon, with its short lifetime, its sensitivity to electromagnetic interactions, and the extraordinary precision with which its magnetic moment can be measured, would be among the first particles to register that interaction as a detectable anomaly. The anomalous magnetic moment is exactly the class of signal you would predict from vacuum perturbation by a neighboring reality structure. Not a new particle with a fixed mass and a definite decay signature. A diffuse, distributed correction to vacuum energy, the kind of thing that shows up as a systematic offset in precision measurements rather than a sharp peak in a mass spectrum. Place an extremely sensitive compass in a room that everyone agrees has no magnetic field. The needle settles. You leave it for an hour. You come back and find the needle has drifted a small but consistent angle from where it was. Not randomly, always the same direction. Always the same magnitude. Every time you reset it, it drifts back to that same offset. Something is pulling it. The room is not as empty as it looks. That is the muon G2 result. A compass that keeps pointing somewhere nobody has looked yet, in a direction the map says does not exist. Two completely independent experiments separated by 15 years Brookhaven in 2006. Fermilab between 2019 and 2023, conducted at different facilities by different research teams using different muon sources and different detector technologies. Both found the same deviation. Both found it in the same direction. The probability of two independent experiments of this precision producing the same systematic offset in the same direction purely by chance is, statistically, negligible. This is not a fluke of one measurement. This is a consistent signal from two independent instruments telling the same story. The standard model is missing something. Something that interacts with muons. Something that leaves a fingerprint in the quantum vacuum. Something that two independent experiments 15 years apart have both detected without being able to identify. The standard model describes, with extraordinary precision, the behavior of 17 fundamental particles across 4 fundamental forces. It predicted the Higgs boson before it was found. It predicted the existence of the W and Z bosons, the gluon, the charm quark, the top quark, all confirmed by experiment. Its track record is, within its domain, essentially perfect. That domain covers approximately 5% of the total energy content of the observable universe. The remaining 95% dark matter, dark energy, the mechanism behind baryon asymmetry, the hierarchy problem, the cosmological constant. None of it is explained by the Standard Model, the model that achieves 12 decimal place precision on muon magnetic moments is simultaneously blind to 95% of everything that exists. Describing the Standard Model's achievement is something like praising a naturalist who spent a lifetime cataloging every species of bubble that forms on the surface of the Pacific Ocean. Extraordinary precision, meticulous methodology, and absolutely no account of the trillion liters of water below. The moon compass is pointing down into that water. The question nobody in the official scientific apparatus has seriously pursued is whether the water below is not just more of our universe, but the floor of a neighboring one. But if the muon G2 is the compass that keeps drifting, the matter-antimatter asymmetry is the question of why the universe exists at all, and the answer may point back to the same place. The Big Bang, according to every theoretical model built on general relativity and quantum field theory, produced matter and antimatter in precisely equal quantities. For every quark that appeared in the first fractions of a second after creation, an antiquark appeared alongside it. For every electron, a positron, perfect symmetry, perfect balance. When matter meets antimatter, both annihilate in a burst of pure energy, photons radiating outward, leaving nothing behind. If the early universe had maintained perfect symmetry all the way through those first critical seconds, every particle would have found its antiparticle partner, every pair would have annihilated, and the universe today would contain nothing but a cooling bath of photons traveling through empty space. No hydrogen, no stars, no galaxies, no periodic table, no planets, no one reading this. We are here. The stars are there. The galaxies exist, which means the symmetry broke. Somewhere in the first second of cosmic history, matter won not by much, but by enough. For every 1 billion matter-antimatter pairs that annihilated each other in those opening moments, one extra particle of matter survived, 1 in a billion. That razor-thin surplus is called baryon asymmetry, and it is the entire reason the observable universe contains anything at all. The mechanism proposed to explain how that asymmetry arose is called CP violation, the breaking of the combined symmetry between charge conjugation and parity. In a perfectly CP symmetric universe, the laws of physics would be identical whether you replaced every particle with its antiparticle and mirrored the spatial coordinates simultaneously. CP violation means that symmetry is not exact. Particles and antiparticles behave in subtle ways differently. CP violation was first observed experimentally in 1964. In the decay of neutral kaons, a discovery that earned James Cronin and Val Fitch the Nobel Prize in Physics in 1980. It has since been measured in B mesons and, more recently, in D mesons. CERN's LHCb experiment, the Large Hadron Collider beauty experiment, a dedicated detector optimized specifically for studying heavy flavor physics, has been measuring CP violation with increasing precision over the past decade. In 2019, LLHCb reported the first observation of CP violation in charm mesons, specifically D0 mesons, at a statistical significance of 5.3 sigma, published in Physical Review Letters. It was a genuine landmark result, confirming that CP violation occurs in a new class of particles, extending the experimental map of asymmetry. But here's the problem, and it is a deep one. The magnitude of CP violation measured across all observed processes, kaon A mesons, D mesons combined, is far too small to account for the baryon asymmetry we observe. Physicists have calculated this carefully. The amount of CP violation the Standard Model permits produces a matter surplus many orders of magnitude smaller than the 1 in a billion ratio that allowed the universe to exist. The Standard Model's CP violation is real. confirmed, and thoroughly insufficient. Something else broke the symmetry, something larger, something the model does not contain. In 2018, Neil Turok and Latham Boyle at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, published a paper in Physical Review Letters proposing a solution that resolves the asymmetry problem in a way no previous model had managed. Their CPT symmetric universe theory proposes that the Big Bang did not produce a single universe. It produced two our universe, expanding forward in time from the moment of the bang, and a mirror universe expanding backward in time from the same point, with matter and antimatter reversed. Viewed from outside, the pair is perfectly symmetric under the combined CPT transformation charge, parity, and time reversal, all applied simultaneously. Viewed from inside either universe, the symmetry appears broken because you can only observe one side of the mirror. Our universe looks matter-dominated because it is. The mirror universe is antimatter-dominated. Together, they are perfectly balanced. This model is not speculative philosophy. It is a mathematically rigorous proposal published in a peer-reviewed journal by researchers at one of the most respected theoretical physics institutions in the world. It accounts for the observed baryon asymmetry without requiring any new particles or any extension of the standard model beyond the CPT mirror structure itself. And it has a specific physical implication for the LHC anomaly. If the mirror universe exists and shares a quantum boundary with our universe at the Big Bang point, a boundary that, under normal cosmological conditions, is inaccessible, then probing energy scales close to early universe conditions brings our instruments closer to that boundary. The LHC at 13 tera electron volts is probing conditions corresponding to approximately a 1/1,000,000th of a second after the Big Bang. It is not reaching the boundary, but in the CPT symmetric framework, it may be close enough that quantum information from the mirror universe bleeds across. The signal that would produce is precisely the bimodal distribution observed in the run-2 4-lepton channel. Two sources contributing to the same event, one from this side of the boundary, one from the other. Picture two cities built in perfect mirror symmetry on opposite banks of a wide river, connected by a bridge that remains closed under normal conditions. Everything in one city is the spatial and temporal reflection of the other. On a quiet day, neither city hears the other. But apply enough weight to the bridge, enough structural stress across the boundary, and vibrations begin to travel. Sounds from the other city bleed through the structure, echoes of music that does not belong to your city, arriving faintly through the bridge supports, blending briefly with your own city's sounds before the vibrations dampen and the boundary reasserts itself. The LHC collision at 13 tera electron volts is that weight on the bridge. The bimodal signal in the 4-lepton channel is those arriving vibrations, and the 100 nanosecond duration is precisely how long it takes for the bridge to stop resonating once the load is removed. Your existence, every atom of your body, every star in the sky you have ever looked at, every galaxy in every direction the Webb telescope points depends on a matter surplus smaller than 1 part in 1 billion that arose in the first second of cosmic history, for reasons that the best theoretical framework ever constructed cannot fully explain. 1 in a billion. That is the margin by which you exist, by which everything exists. And after more than a century of physics, after the LHCb's landmark measurements of CP violation in D mesons, after the most precise experiments ever conducted on the question we still do not know why that margin exists, we know it does. We can measure its consequences. We cannot explain its origin within the standard model. Honestly, the entirety of human existence is effectively a rounding error in the universe's arithmetic. 1 extra particle per billion that the calculation forgot to cancel. The gaps in our current understanding are not small questions waiting patiently in a queue. They are warnings, and CERN is about to turn the intensity up by a factor of 5 to 7. The LHC currently operates in what physicists call Run 3, which began in 2022 and is scheduled to continue through 2025. During this phase, the machine runs at a collision energy of 13.6 tera-electron-volts, the highest sustained energy ever achieved in a particle collider, and reaches a peak luminosity of 2 × 10 to the power of 34 collisions per square centimeter per second. Luminosity is the metric that measures how densely packed the collisions or how many proton-proton interactions occur per unit of detector area per unit of time. Think of it as the intensity dial on the machine. Higher luminosity means more collisions per second, more data per hour, more statistical power to detect rare processes. The Higgs boson discovery in 2012 required years of data collection at lower luminosity because the Higgs appears in only about 1 in 10 billion collisions. More luminosity means more Higgs events, more precision measurements, and in theory, more sensitivity to rare new physics signals hiding in the data. This is the scientific rationale behind the high luminosity LHZ, or HLLHZ. The upgrade project is fully underway. Installation of new components began in 2025. First physics operations are targeted for 2029. The official price tag is 950 million Swiss francs, approximately $1,050 million US. The stated scientific goals are clear and legitimate. Collect 10 times the total integrated luminosity of the current LHC program, enabling precision measurements of Higgs boson properties at the percent level, and expanding the search reach for new physics processes with very small production rates. The luminosity target for HLLHC is 7 to 10 × 10 to the power of 34 collisions per square centimeter per second, 5 to 7 times the current peak, sustained, continuous, for years. What is critical to understand and what the official communications about HLLHC do not always make prominent is that the collision energy is not changing. The HLLHC will still collide protons at 14 tera-electron-volts, the same energy regime as the current machine. The fundamental physics of each individual collision remains the same. What changes is the rate, the density, the relentlessness of it. In the current LHC, each time 2 proton bunches cross inside the detector, an event called a bunch crossing, occurring 32 million times per second between 20 and 40 individual proton-proton collisions, happen simultaneously. 40 collisions happening at once is already extraordinarily complex for the detector systems to disentangle. The analysis software must reconstruct which particle tracks came from which collision, a computational challenge that pushed detector design and machine learning algorithms to their limits when the LHC was first built. In the HLLHC, each bunch crossing will produce between 140 and 200 simultaneous collisions per crossing, 32 million crossings per second. That is not an incremental increase. It is a qualitative transformation in the density of the collision environment, a state of continuous, overlapping, compounding quantum events at extreme energy that has no precedent in the operational history of any particle accelerator ever built. Now apply the branch echo framework from Part 5 and Part 6 directly to these numbers. If branch echoes are produced by stress on the quantum vacuum, by the localized energy density generated when protons collide at 13 to 14 tera-electron-volts, then the rate of vacuum perturbation scales with luminosity. More collisions per second means more stress events per second. More stress events means more frequent puncturing of the vacuum membrane. If the current LHC is producing vacuum perturbation at some baseline rate, The HLLHZ produces that perturbation at 5 to 7 times the rate, continuously, not in brief operational runs, but in sustained physics fills lasting many hours, repeated across years of operation. The current LHC's anomalous signals, the 100 nanosecond ghost hits. The bimodal structure in the 4-lepton channel appeared during high luminosity runs at the start of run 2. When the machine was pushing into energy territory it had never previously occupied. The HLLHC will operate at 5 to 7 times that luminosity as its normal operating condition, not its peak, its baseline. If there is even a 1% probability that the LHC has been periodically stressing the quantum boundary between adjacent reality structures, then the HLLHC multiplies that probability by a factor of 5 to 7 and sustains it continuously across more than a decade of operation. Basic risk mathematics does not require you to believe the 1% is real in order to conclude that it demands a serious, independent, formally conducted investigation before the machine enters service. 1% of a catastrophic outcome, multiplied by 7 and extended over 12 years, is not a rounding error in a risk ledger. In any other engineering context, aerospace, nuclear power, pharmaceutical trials, civil infrastructure, that calculation triggers a formal review process. A review process that examines the specific failure mode in detail, that seeks independent expert assessment, that produces a public report with a reference number that anyone can read. Imagine you are driving a nail into a wall. After a dozen strikes, a strange sound comes back, not the clean resonance of a nail hitting solid material, but something hollow, something that shouldn't be there, a cavity, perhaps, something unexpected behind the drywall. The reasonable response is to stop, to probe the wall, to find out what is behind it before you continue. Instead, you set down the hammer, walk to the hardware store, and return with an industrial pneumatic drill. Because you have more nails to drive and the schedule does not permit a detour. That is the operational logic of proceeding with the HLLHC upgrade while the anomaly data from Run 2 remains uninvestigated. The strange sound from the wall has been logged as acoustic artifact of uncertain origin, and the drill is already running. CERN has invested approximately $10 billion in the LHC program across its full lifetime of design, construction, and operation. The HLLHC adds another $1,050 million on top of that. The financial scale of the commitment is staggering, and financial commitments of that magnitude create their own gravitational field. They pull decisions toward continuation, toward the next phase, toward the project as defined, rather than toward the questions the data is raising. The issue is not whether CERN can afford the HLLHC. Clearly it can. 23 member state governments have already committed to funding it. The issue is whether the scientific and ethical framework around the project is commensurate with the questions the existing data has raised and left unanswered. Money is not the constraint. Caution is. In engineering, the principle is well established: if it is not broken, do not fix it. Particle physics appears to operate on the inverse philosophy: if you do not yet understand it, increase the power and see what happens next. But the larger risk is not what might happen inside the detector. It is what is not being said outside of it. In the summer of 1945, in the weeks before the Trinity test, the first detonation of a nuclear device in the desert of New Mexico, Enrico Fermi offered to take side bets from other scientists on the project. The question he posed: would the nuclear explosion ignite the atmosphere? Would a self-sustaining chain reaction in the nitrogen of Earth's air be triggered by the detonation, consuming the entire atmospheric envelope of the planet? The answer, according to the theoretical calculations done by Hans Bethe and others, was no. The probability was vanishingly small. The physics was understood. But Fermi offered the bet anyway, not because he believed the atmosphere would ignite, but because he was, with characteristic precision, acknowledging that the calculation was based on models, and models have edges that no one has fully mapped. The bomb went off. The atmosphere did not ignite. The models were right, but the fact that the most careful physicist of his generation paused before the first test of a device whose physics he understood deeply and thought it worth gambling $10 on the possibility that he was wrong about something that instinct is worth holding on to, especially now. CERN has conducted formal safety assessments of the LHC program on 2 occasions in 2003 and again in 2008, specifically addressing the concern that high-energy proton collisions might produce microscopic black holes capable of growing and consuming matter. Both assessments concluded, correctly, that the LHC presented no such danger. The arguments were rigorous cosmic rays of far greater energy than those produced by the LHC have been striking the Earth, the Moon, neutron stars, and white dwarfs for billions of years without catastrophic consequence. If stable black holes of the dangerous variety could be produced at LHC energies, the universe would have shown evidence of the effect long before any human accelerator was switched on. Those assessments were sound. The conclusions were justified. The LHC did not produce dangerous black holes. The models were right about that. But both assessments were conducted entirely within the framework of the Standard Model of particle physics. They evaluated risks that the Standard Model could define. They examined failure modes that known physics could generate. That is the only thing a safety assessment can do. It can assess the risks it knows to ask about. Donald Rumsfeld, in a different context entirely, articulated the epistemological problem with unusual clarity. There are known knowns, things we know that we know. There are known unknowns, things we know that we do not know. And there are unknown unknowns, things we do not know that we do not know. The CERN safety assessments of 2003 and 2008 addressed known unknowns within the Standard Model framework. They could not, by definition, address unknown unknowns that the Standard Model does not contain. If the anomaly data from Run 2 indicates that there is physics operating at LHC energies that lies outside the Standard Model and the bimodal 4-lepton signal, if genuine, is precisely that kind of indication, then the safety assessments built on the Standard Model are not wrong. They are systematically incomplete. There is a category of risk they were structurally incapable of evaluating, because the theoretical tools required to define that risk did not exist within the framework used to conduct the assessment. The history of technology offers a precise parallel. Chlorofluorocarbons, CFCs, were developed in 1928 by Thomas Migley Jr. at General Motors as a refrigerant to replace the toxic and flammable gases then used in cooling systems: ammonia, sulfur dioxide, propane, all dangerous in the context of household refrigerators. CFCs were stable, non-toxic, non-flammable, and chemically inert under normal atmospheric conditions. They were, by every measure available to chemistry in 1928, the perfect safe solution. For 50 years, they were used without incident in refrigerators, in aerosol cans, in air conditioning systems, in industrial processes worldwide. The risk assessments conducted throughout that period found nothing dangerous. The chemistry was well understood. The models were right about everything they measured. What the models could not measure, because the question had never been asked, was what happened to those stable, inert molecules when they drifted up to the stratosphere and encountered ultraviolet radiation. Nobody in 1928, or 1948, or 1968 thought to ask that specific question. It fell into the unknown unknown zone. It was not concealed. It was not dismissed. It simply did not exist as a question within the frameworks that were doing the risk assessment. In 1974, 46 years after CFCs entered widespread use, Mario Molina and F. Sherwood Rowland published their landmark paper demonstrating that CFCs were destroying the ozone layer. By that point, the compounds had been accumulating in the stratosphere for nearly half a century. The damage was already done. The lag between the action and the discovery of the consequence was 46 years. The HLLHC is designed to operate through at least 2041. That is 12 or more years of 5 to 7 times the current luminosity. 12 years of continuous, sustained vacuum perturbation at rates that dwarf anything the current LHC has produced. If there are consequences to operating at that intensity, and if those consequences accumulate gradually rather than manifesting immediately, the operational timeline of the HLLHC creates exactly the kind of extended lag that made CFCs so damaging. By the time a pattern became clear enough to investigate seriously, the machine would have been running for a decade. The European Physical Society and the American Physical Society, the two largest professional organizations representing physicists on their respective continents, have issued no statement regarding the Run-2 anomaly, no position paper, no call for independent investigation, no formal acknowledgement that the bimodal signal in the 4-lepton channel is a matter requiring institutional attention. That silence is not because these organizations considered the question and found it unworthy. It is because the anomaly was never published. A question that does not exist in the public scientific record cannot be formally addressed by professional organizations that respond to published science. The decision not to publish closed the loop before it could open. Before the European Physical Society could convene a panel, before the American Physical Society could form a working group, before any independent physicist outside the collaboration could request access to the relevant dataset for verification. The decision to classify the anomaly upstream of the publication pipeline did not just prevent one paper from being written, it prevented the entire institutional apparatus of independent scientific oversight from activating. Every organization that might have asked the right questions was structurally prevented from knowing the questions existed. Building the HLLHC, while this remains, the situation is something like deciding to construct a massive dam on a river without drilling a single geological survey borehole first, not because the geology is unimportant, but because the engineers on the project never thought to ask what kind of bedrock was down there. And the people who noticed something unusual in the initial survey data filed it under inconclusive ground conditions before anyone else saw it. The dam may be fine, the bedrock may be solid, but the decision was made without the information that would have confirmed it. In some sense, humans are the only creatures in the known universe capable of looking at anomalous data from a reality boundary probing machine and concluding that the most rational next step is to build a larger one. That is either extraordinary courage or extraordinary innocence. Perhaps both, in the specific ratio that has always characterized the most consequential decisions in scientific history. But the deepest question here is not whether the machine is dangerous. It is who was given the authority to decide that, and who was never asked. Galileo did not own his observations of Jupiter's moons. He recorded them, he published them, and the Church decided what would happen next. The question of who controls scientific knowledge, who gets to determine what is known, what is investigated, what is allowed to exist in the formal record, is not a modern problem invented by bureaucracy. It is as old as organized inquiry itself. What has changed is the scale. In Galileo's time, one man with a telescope and a printing press could bypass institutional authority if he was willing to accept the personal consequences. Today, the instruments that probe the deepest questions about physical reality cost $10 billion, require 23 governments to fund them. and employ 17,500 scientists whose professional survival depends on the approval of the same institutions that control what those instruments are allowed to find. That is not a conspiracy. It is a structural reality. And structural realities produce predictable outcomes regardless of whether anyone intended them. CERN's official policy on scientific results is unambiguous. The organization describes itself as committed to open access, the principle that all research produced using public funding must be made freely available to the public. Every paper published by CERN collaborations is deposited in open repositories. Every data set, once formally processed and approved, is eventually released through the CERN Open Data Portal. The stated philosophy is that knowledge produced by the taxes of 23 nations belongs, in some meaningful sense, to the citizens of those nations, not to the institution, not to the collaboration, to the public. That policy, as written, is admirable. As practiced, it contains a gap wide enough to swallow an anomaly whole. Open access applies to results that enter the publication pipeline. The classification decision the moment when data quality assessment labels a signal structured background of unknown origin and routes it away from formal analysis happens upstream of the pipeline entirely. A result that never enters the pipeline can't be blocked from publication because it was never a candidate for publication to begin with. No policy is violated. No procedure is circumvented. The system functions exactly as designed, and the anomaly ceases to exist as a scientific object. It becomes, in the official record, nothing, not a finding, not a hint, not even a formally documented negative result. Nothing. This is what philosophers of science call epistemic injustice. The term was developed by Miranda Fricker in her 2007 work, Epistemic Injustice, Power, and the Ethics of Knowing. And it describes a specific form of harm that occurs when structural power prevents participation in the production of knowledge. Fricker's original formulation focused on how individuals, particularly those from marginalized groups, are systematically excluded from having their testimony credited, their observations taken seriously, their voices heard in the processes by which societies decide what is true. The mechanism she describes is not always malicious. It does not require a villain. It requires only that the people with institutional authority to validate knowledge are operating within frameworks that systematically disadvantage certain kinds of claims. Apply that framework to the run-to anomaly, and the fit is uncomfortably precise. The 17,500 scientists working with LHC data are not the ones who made the classification decision. The global physics community, the independent researchers at universities across 100 countries who might have asked different questions, never received the data. The 23 governments whose taxpayers funded the machine have no mechanism to demand an accounting of what the machine found and chose not to investigate. The entire scientific community was placed, by a data quality decision made at the collaboration level, in the position of not being able to know something they needed to know. That is epistemic injustice operating at civilizational scale. The decision-making structure at CERN distributes authority in a way that makes this outcome structurally likely, if not inevitable. At the top sits the CERN Council, the governing body composed of representatives from the 23 member states, meeting twice yearly to set policy and approve budgets. Below that is the Director General, currently the chief executive authority for the organization's scientific and operational direction. Below that are the Research Board and the various collaboration structures, Atlas, CMS, LHCB, Alice, each with their own internal hierarchy of working groups, editorial boards, and spokespersons. The critical point decisions about data quality are made at the collaboration level, not the council level. The 23 governments that fund the program have no direct visibility into or authority over, the process by which specific signals are classified and routed. The research board reviews published results, not pre-publication classification decisions. The accountability chain between the taxpayers of Germany, France, Italy, and the United Kingdom, and the data quality decision that determined what their investment in the LHC was and was not permitted to find, is not just long. It is, for all practical purposes, broken. This structure has produced catastrophic outcomes before. On January 28, 1986, Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew members. The Rogers Commission investigation that followed revealed something that has haunted engineering ethics ever since the engineers at Morton Thiokol, who built the solid rocket boosters, knew about the O-ring failure risk. They had documented it. They had flagged it. The night before the launch, several of them argued strenuously against proceeding in cold temperatures. The data was clear to the people who understood it. But the decision to launch was not made by the people who understood the data. It was made by a management layer, structurally separated from the technical layer, operating under schedule pressure, institutional momentum, and the desire to demonstrate operational reliability. The engineers' warnings did not reach the people with launch authority through the channels that would have given them institutional weight. The disconnect was not dishonesty. It was architecture, a decision-making structure that separated technical knowledge from operational authority, and then trusted the gap to resolve itself. The gap did not resolve itself. 7 people died. The parallel to the Run 2 anomaly is not about death. The stakes are different in every obvious sense, but the structural mechanism is identical. Technical observations, the ghost hits. The bimodal 4-lepton signal were made by the people closest to the data. Those observations were processed through a decision layer that prioritized institutional continuity over anomaly investigation. The information never reached the level at which a different decision could have been made. The Council never voted on it. The member state governments were never informed. The global physics community was never given the chance to examine it independently. The data quality layer absorbed the anomaly, and the rest of the system continued forward as though nothing had happened. Because for every part of the system above that layer, nothing had. Scientific data about the physical structure of reality does not belong to CERN any more than a nautical chart belongs to the ship that first sailed that water. The ship can keep the chart locked in a drawer, but the ocean is still there, the shoals are still there, and every vessel that follows without a chart is navigating blind through waters that someone already mapped and chose not to share. 17,500 scientists are working with LHC data. Not one of them has published an independent analysis of the bimodal anomaly in the Run 2 4-lepton channel. That level of uniform silence across a community that size has occurred exactly twice in the history of organized science, when there was genuinely nothing interesting to find, and when there was something so interesting that the institutional consequences of finding it outweighed the scientific obligation to report it. You know which option requires the simpler explanation. And here is what makes it strange in a way that transcends the physics entirely. When a particle physicist encounters a result that does not fit the model, the standard emotional response documented across decades of conference presentations, collaboration meetings, and late-night data sessions is excitement, not anxiety, not caution, excitement. The anomaly is the prize. It is what the machine was built to find. A community of 17,500 people wired by training and temperament to pursue the unexpected. And not one of them published a word about a 2.8 sigma bimodal anomaly in the most trusted channel in the field. That is not the behavior of scientists who found nothing interesting. That is the behavior of people who received a message without anyone needing to send it. When physicists go quiet, it is because they are being careful. When all of them go quiet at once, it is because the institution is being careful. And when an institution that employs 17,500 of the most curious human beings alive manages to produce collective silence about an anomaly of this character, that is not a scientific response. That is the behavior of a legal department. But the problem is not that CERN is malicious or that its scientists lack integrity. The problem is what the system was designed to reward, and how that design produces silence as a natural and entirely predictable output. Science, as an ideal, works like this. A researcher observes something, forms a hypothesis, designs an experiment, collects data, submits the results to peer review independent experts who examine the methodology, probe the statistics, and challenge the conclusions without any stake in the outcome. The paper is published. Other researchers attempt to replicate the result. Consensus forms or doesn't, based on the accumulated weight of independent verification. The system is, in principle, self-correcting. No single authority controls what is true. The truth emerges from the collision of independent efforts. That system produced quantum mechanics, the germ theory of disease, the double helix, the Higgs boson. It is the most successful method for producing reliable knowledge that human civilization has ever invented. It is also, like every human institution, subject to the pressures that shape the behavior of the people operating within it. And in particle physics specifically, those pressures have grown over the past several decades into something that a careful observer would have to call structural. Academic survival in high-energy physics is measured in publications and citations. A postdoctoral researcher needs papers. A junior faculty member needs papers and grants. A senior physicist needs a publication record sufficient to justify the position, the salary, the graduate students, and the next round of funding. This is not a peculiarity of physics. It is the common currency of academic science worldwide. Publish or perish is not a metaphor. It is an operational description of how careers are built and ended. The problem, in the specific context of a collaboration like ATLAS or CMS, is that publications are not individual acts. Every paper from the LHC collaborations carries hundreds of authors, sometimes over 3,000, for major results. Every paper must pass through the collaboration's internal review process before submission working group approval, editorial board review, statistics committee sign-off, spokesperson authorization. This process exists for good reasons. In an experiment of this complexity, with this many contributors and this much at stake scientifically, some form of coordinated quality control is necessary. Nobody disputes that. But the same mechanism that ensures quality also concentrates gatekeeping authority in a small number of people. The spokesperson of ATLAS and the spokesperson of CMS are, effectively, the final editorial authority for what their collaborations publish. The editorial boards they oversee shape the internal culture of what is worth pursuing. A junior physicist who identifies an anomaly that the editorial board is not inclined to investigate has no alternative route. There is no internal appeals process. There is no mechanism by which a working-level physicist can formally escalate a data quality classification decision to a higher authority within the collaboration. The pipeline is linear, and the gates are controlled by the same institutional culture that classified the anomaly to begin with. No written policy forbids pursuing the bimodal anomaly. Nobody issued a memo. What happened is subtler and more durable than a directive. The classification was made. The working groups moved on to other analyses. The agenda of collaboration meetings did not include time for a discussion that had, in effect, already been concluded. A junior physicist watching that process learns, without needing to be told, what is and is not a viable path for their career. The institutional temperature communicates the message that no formal communication needs to deliver. The Fleischmann-Ponce cold fusion episode of 1989 illustrates how quickly a scientific community can collectively decide, with insufficient evidence, that a result does not merit serious investigation. In March of that year, Stanley Ponce and Martin Fleischmann announced at a press conference that they had achieved nuclear fusion at room temperature in a tabletop apparatus. The claim was extraordinary. The evidence was contested from the outset. Multiple laboratories attempted replication and failed to reproduce the results. Within months, the community had largely concluded the claim was false. Whether that conclusion was correct, the question of anomalous heat production in certain electrochemical systems remains scientifically unsettled in ways that are rarely acknowledged is less important for this discussion than the speed and totality of the rejection. Many physicists who participated in that period have since acknowledged, with some discomfort, that the community's response had elements of what one researcher described as mob dynamics, a rapid collective decision, driven partly by reputational concerns and partly by the professional cost of being associated with a discredited result. That foreclosed investigation faster than the data actually warranted. The lesson is not that cold fusion was real. The lesson is that peer review, operated by human beings with careers and reputations, can produce consensus that outruns evidence in either direction. In the natural sciences more broadly, replication studies have found that somewhere between 10 and 15% of published findings cannot be reproduced under controlled conditions. Physics sits at the rigorous end of that spectrum. Its standards for statistical significance are higher. Its measurement protocols more formalized. Its results more frequently verified by independent experiments. But the number is not zero. No system staffed by human beings with institutional pressures is immune to systematic bias. The LHC is not special in that regard. It is, if anything, more vulnerable to certain forms of bias precisely because of its size. The concentration of authority in a small leadership layer over a very large community creates conditions where the gap between what is found and what is reported can widen without anyone in the majority of the collaboration necessarily noticing. Philosophers of science who study large-scale research infrastructure have proposed structural solutions to exactly this problem. Independent data review boards, analogous to the FDA's independent advisory committees, which evaluate pharmaceutical trial results without institutional ties to the companies running. The trials have been proposed as a mechanism for reviewing anomaly classifications before they are finalized. Mandatory pre-registration of anomaly investigation protocols requiring collaborations to publicly commit before data collection begins to how they will handle signals in specific channels at specific significance levels would prevent post hoc classification decisions from remaining invisible. Expanded open data access for verified independent researchers with computational resources sufficient to actually perform alternative analyses would allow the 17,500 insiders to be supplemented by external perspectives, not subject to internal career pressures. None of these mechanisms exist for the LHC anomalies. None of them were applied to the run-to bimodal signal in the 4-lepton channel. None of them are currently part of the governance framework for the HLLHC. The current structure resembles a court of law in which the judge, the prosecution, and the jury are drawn from the same organization, and the appeals court has no subpoena power over the evidence. This is not a failure of good intentions. The people who built this system built it with the goal of producing the best possible physics from the most complex instrument ever constructed. They succeeded by almost every measure. The system is extraordinarily good at what it was designed to do. What it was not designed to do, what no one thought to design it to do, is investigate anomalies that the institutional culture has implicitly decided are not worth investigating. A system that excellent at its intended purpose does not automatically develop the capacity to audit its own blind spots. That capacity has to be deliberately built in. It was not, And the absence is not incidental. It is load-bearing. The question worth asking is not whether CERN is concealing something. The honest and more disturbing question is whether the system was ever designed to make concealment impossible, to make the investigation of deeply inconvenient anomalies structurally mandatory rather than institutionally optional. The answer, examined without illusion, is no. And a system that does not compel investigation of anomalies that nobody has career incentives to pursue is a system that will reliably, predictably, and without any individual acting in bad faith, produce silence about exactly those anomalies. In every other domain of human life, when you do not understand something, the advice is consistent. Ask an expert. In particle physics, when the experts encounter something they do not understand, the apparent standard procedure is to rename it a background noise and move to the next item on the agenda. The final point, and perhaps the most important one, is not about CERN or about the data at all. It is about what kind of questions we allow ourselves to ask. Galileo did not set out to threaten anyone. He pointed a telescope at Jupiter, recorded what he saw, and an institution decided his data was dangerous. Copernicus died the year his model was published. Darwin waited 20 years before releasing his theory, knowing exactly what reception awaited it. In every era where genuine inquiry pressed against the limits of the dominant framework, the question was treated first as a threat and only later, sometimes centuries later, as the gift it actually was. The pattern is not incidental. It is the most consistent feature of scientific history, not the discoveries themselves, the resistance, the institutional decision that certain questions are too destabilizing to be formally asked, made every time by people who were not stupid or malicious, but who had enormous stakes in the continuity of the framework they were protecting. And every single time, the question was eventually asked anyway. Every framework broke open and became something larger. Not once, in the entire record of science, has the expansion of understanding made the world worse for having happened. That is not a hypothesis. That is the actual record. The instruments of 21st century science operate at scales those earlier figures could not have imagined. The Large Hadron Collider spans 27 kilometers beneath 2 sovereign nations, funded by 23 governments, operated by a workforce larger than most universities. The James Webb Space Telescope sits 1.5 million kilometers from Earth, imaging the first galaxies that formed after the Big Bang with resolution considered physically impossible 2 decades ago. No single nation controls these instruments. No single institution can fund them alone. They are collective enterprises, expressions of a shared human ambition, and that collective origin carries a collective obligation. The concept of responsible innovation, developed over the past 2 decades by scholars including René von Schomburg at the European Commission and Richard Owen at the University of Exeter, holds that large-scale research programs capable of producing transformative or irreversible effects must incorporate anticipatory thinking, reflexivity, and genuine public accountability into their core governance, not as public relations, but as design requirements. CERN has formally endorsed principles consistent with this framework in multiple policy statements. The distance between those stated commitments and the operational reality described across the preceding parts of this account is not a small gap. It is a structural contradiction at the center of how the organization handles exactly the kind of anomaly responsible innovation was designed to address. The public that funded this machine has a democratic claim on what it found, not a technical claim. Citizens do not need access to raw detector files, a civic claim. In any system where citizens fund scientific research through taxation, there is an implicit contract. The knowledge produced belongs, in a meaningful sense, to the people who paid for the search. The taxpayers of Germany, France, Italy, the United Kingdom, and 19 other nations funded the instrument that recorded the bimodal anomaly in the Run-2-4-lepton channel. None of them were told it existed. Their elected representatives were never asked to consider it. Their children's generation, who will inherit the HLLHC and its 12+ years of 5 to 7 times current luminosity, will do so without ever having been told that the previous machine found something it could not explain and chose not to investigate. This is not about fear. The history of scientific progress is not a story of humanity bravely confronting a hostile universe. It is a story of humanity repeatedly discovering that the universe is larger, stranger, and more astonishing than the previous framework allowed, and finding, each time, that the expansion was worth every disruption it caused. Heliocentrism placed us in a solar system, then a galaxy, then a cosmos of staggering scale and beauty. Evolution embedded us in 4 billion years of life's elaboration across an entire planet. Quantum mechanics revealed that reality at its foundations is stranger and more wonderful than anything classical physics had dared imagine. Every one of those expansions required accepting that something fundamental had been wrong. And every time, that acceptance was not defeat. It was maturity. What is lost when an anomaly goes uninvestigated is not merely one paper, one signal, one missed data point. It is the opportunity for that maturation to occur, the chance for human understanding of its own position in the physical universe to take one more step towards something truer. Each time an institution chooses the comfort of an existing framework over the discomfort of a genuine anomaly, it is not making a scientific decision. It is making a decision about what kind of civilization we are, one that follows the evidence wherever it leads, or one that follows it only as far as existing incentives permit. Refusing to investigate a quantum anomaly because it does not fit the model is like seeing a strange light on the horizon, deciding it is an atmospheric artifact, and never walking out to see what is actually there. The label costs nothing. The walk might cost everything you thought you knew. Apparently, that is the price that feels too high. If the data from the Large Hadron Collider genuinely indicates the existence of 2 interacting streams of reality, even if the probability is only 1 in 1,000, that would be the greatest discovery in the history of human civilization. Greater than heliocentrism, greater than evolution, greater than quantum mechanics itself. A confirmation that the universe we inhabit is one branch among many, that the boundary between branches is physically real and briefly permeable under conditions we can engineer. That discovery was within statistical reach of a formal investigation into a 2.8 sigma signal in the cleanest detection channel in experimental physics. It was placed in a discard pile not after investigation, not after refutation, but before either labeled structured background of unknown origin and routed away from every process that would have compelled a response. If that does not produce outrage, it must at least produce a question. And this is where we stand, not at the end of the story, but at the beginning of a question that all of humanity has not yet been permitted to ask in full. Step back for a moment. A 100 nanosecond ghost signal in a tunnel 27 kilometers long. A bimodal anomaly in the cleanest detection channel in physics, confirmed by 2 independent instruments, sitting at 2.8 sigma before someone stopped counting. A muon compass pointing somewhere the map says does not exist. A matter surplus smaller than 1 part in 1 billion that is the sole reason anything in the universe exists at all. Collective memories drifting in ways that cognitive science can partially explain and cannot fully account for. 4 independent theoretical frameworks converging from 4 different directions on the same prediction, all of it pointing at one question: where exactly are we in this universe, and are we genuinely willing to find out? This is not a conclusion that 2 timelines are real. It is not a verdict on whether CERN is hiding something. Both of those framings are too small for what is actually at stake. What deserves recognition is something larger. We are living in the first period of human history where the question of how many branches of reality exist is no longer the exclusive property of philosophy or science fiction. It is a question that may have experimental data attached to it. That is an extraordinary thing. It should be treated as one. The greatest figures in the history of science were not the ones who arrived with answers. They were the ones who held a question long enough, carefully enough, stubbornly enough, that the universe eventually had no choice but to respond. Mystery is not the enemy of understanding. It is the condition that makes understanding possible. The next time you remember something wrong, a small detail from the past that nobody else recalls the same way, a word spelled differently than you were certain it was, a line from a film that turns out never to have been said, it is probably a false memory. The cognitive science on that is solid and well earned, but possibly, just possibly, it is an echo from the edge of a neighboring branch of reality, where a different version of this story is being told in a different way. We do not know, and that not knowing still intact, still open, still waiting, is the most beautiful thing science still possesses.